Okay, good morning to everyone. Now, today in last class, we have seen about the topic of the pipelining and what are the hazards that occur in the pipeline. We have already seen it. So today we will start another topic. This is related with the cache mapping, that the cache memory that is present in our system, and how the mapping, how with CPU, from CPU it generates the address, and how this address are mapped, we will see that. Now cache mapping is what we have: three types of cache mapping: direct mapping, fully associative mapping, and keyway set associative mapping. Now before starting this, let's see what are in our system, how its architecture is given in our normal system, how the architecture is present. Now basically in our system there will be a CPU present. Like this, there will be a CPU or the processor present, and with this a cache memory is connected. With this a cache memory is connected, or we can say the cache memory is embedded over the CPU. Now this cache memory is what this cache memory will be connected with RAM, and means random access memory. With this a cache memory will be connected, and this RAM will be connected with our hard disk, that is our secondary memory, that means the full storage. So like this, in our system the architecture is present, that a cache memory is embedded over the CPU, and the cache memory is connected with this RAM, and a RAM is connected with the secondary memory. So this is the internal architecture of our any of our system. Now what, all the programs, the total full program is stored into this our secondary memory or the hard disk. In hard disk the total full program is stored. Now this full program is stored into the secondary memory. Now this secondary memory has the amount of storage is much more. This secondary memory storing capacity is large, so that's why the full program is stored into our secondary memory. But whether our cache memory is what, the cache memory is storage is very much less. So that means what, all total full program we cannot at a time accommodate in our cache memory. So how we will do? The full program that is stored into our secondary memory, from there some portion of the program will be brought to the RAM. From secondary memory, some portion, the total program is stored into our secondary memory, and from there some portions of the program will be brought to the RAM, and from RAM some portion of the program will be brought to the cache memory, because we cannot totally accommodate the full program at a time into the cache memory, because cache memory storage is very much less. So after that, when it will go to the cache memory, some portion of the program which goes to the cache memory, then CPU will do what? CPU will access that, or the processor will access that, and it execute. So after the execution, then again some portions will be brought, and then it will be transferred to the cache memory, and then CPU will execute that portion. So like this our total happen. Then the thing, that question arises, that we can totally transfer this totally transfer the program from secondary memory to the CPU, or CPU can access the total secondary memory. This can happen. Then why are we using this level of memory, that some portion brought to the RAM, then from there some portion brought to the cache, and then CPU access that and execute it? So it is why this is happening, because CPU, mainly this level of memory is used because CPU works in the MIPS or GIPS because CPU speed is much more. CPU works on MIPS, that means mega instruction per second or the million instruction per second. That means it is, if we convert into our numerical form, that is 10 to the power 6 instruction per second. So that means 10 to the power instruction it's execute per second. Or GIPS, that means giga per second, or that means 10 to the power 9 instruction per second. So CPU works very much fast. Whether our secondary memory works on millisecond, that means the CPU works in our millisecond. CPU is working, but the hard disk take the millisecond. So that means the speed difference is very much between our hard disk and our CPU. So that means CPU works in millisecond, or we can say CPU works in the microsecond, but our hard disk work on what? Our hard disk is working in the millisecond. So that means speed difference is much more between them. So that's why some portion of the program is brought into the RAM, because RAM works much more faster than the secondary memory. Then some portion are brought to the cache memory, because cache memory is what it is associated, or this cache memory is embedded over the CPU. So that's why that means they are CPU speed and the cache memory speed is what? Almost same. Something that it differs, but we can say that cache memory speed and the CPU speed is almost same. So that's why if we didn't use this level of memory architecture, then that means CPU will work much faster, and secondary memory will what? Secondary memory will work much slow. So that means the problem will happen. To this normalization, to normalize this problem, we have used this level of memory hierarchy. So that's why some portion we brought into the RAM, and from RAM we brought into the cache memory, and from cache it go the CPU process the instruction. But then you can say that whether we there is why we will use the secondary memory, because secondary memory is no work because its speed is much less, but CPU works on much faster. Then what is the purpose of using the secondary memory? We can, let's say we can use multiple uh, cache memory or the multiple RAM. Then what? Then this problem may not happen, because secondary memory usage is not good. Then why we will use the secondary memory? Because secondary memory we will use, secondary memory storage is much more. Now if we convert it into the cache, then cache or RAM is not so much large amount of data can be stored into the cache or our RAM, whether it can be stored into the secondary memory. Then if we want to accommodate, if we want to remove the secondary memory, then we have to use multiple cache and multiple RAM in our system then. And if we use, because RAM and cache works much more faster, so why this working is much more faster, then the cost will be what? The cost will be increased. So that means if you want to buy a laptop or buy a system, then the cost will be over. If we use multiple cache or multiple RAM, then the cost of the system will be over 1 lakh, 2 lakh, because this the cost will be increased. So to make this normalization process, what we have done to make this total normalization, this level of memory is used, that there will be a secondary memory, a RAM and a cache and a CPU. Some portions will be brought to the memory on the RAM, and from there some portions will be brought to the cache, and what CPU will execute that, so that the program will be executed. So then that portion is completed, then next portions will come, this will be executed, and total the full result will be shown. So this is why we use this is the uses of the cache memory. Okay, it is clear. It is
Yes,
clear
sir.
to everyone.
Yes,
Yes,
sir.
sir.
Okay, so that's why we use the uses of our cache memory, and we cannot use multiple cache or multiple RAM, because if we use, then so much the amount that our secondary memory stored, the amount of data the secondary memory stored, to accommodate that we have to use multiple cache or multiple RAM, because cache and RAM is what secondary memory size is terabyte. It works in the terabyte, but it can store data of the terabyte. But cache memory size is megabyte and RAM is of gigabyte. That if we have to accommodate such large amount of data, then that means we have to use multiple cache to provide this terabyte data, or the multiple RAM to provide this total accommodate this terabyte data, and the cost will be increased. So that's why this level of memory hierarchy is used. Now, basically, in the RAM or the memory we have seen, in this RAM is divided into the multiple logical blocks. RAM is divided into multiple logical blocks. And we use in the RAM, if we see in the RAM, in this RAM, we uses multiple blocks in RAM. It is divided into multiple blocks. Now, RAM, we know that in RAM, the data will be like bytes. So data, we know that in bytes. Now, in computer architecture, we consider 1 byte equal to 1 word. In it is same, we consider that byte in the computer architecture nomenclature, we use the word instead of byte, words. So that means when we will say that our RAM is 128 bytes, the RAM can store 128 bytes data, then 1 byte is equal to what? 1 word. So that means we can say RAM is 120 words. This word is same as byte, but in our computer architecture, we use that word byte instead of word instead of byte. So let's say now the cache mapping. What is the cache mapping? We will understand. Now that is the minimum word is what? What is the minimum addressable unit of the memory? Now cache mapping is what? It is to make the block available in the cache and put it into which line, and CPU generates address to how to make reference to that address to cache to get the data. This total procedure is called the cache mapping. Now first mapping is the direct mapping. So first we will discuss what is the direct mapping. So let's say this is our main memory or the RAM present. This is our RAM or the main memory. Now we have said that in RAM, the data is stored into blocks. The data is stored into blocks. Now, this RAM is what? This RAM has 128 words. That means 120. This RAM has the capacity of 128 bytes. And we know 1 byte equal to 1 word. So this RAM has the capacity of storing 128 bytes, or we can say 128 words. Now in RAM, we say that the data stored into as a block. So that means, and here we are considering that each block can be capable of storing 4-bit data. Each block or 4 word, we can say in computer architecture word that each block can store 4 words or 4 bytes. Each block can store. So that means our total is what? Our total is 128 words. or 128 bytes. And how many words can a block accommodate? A block can accommodate 4 words, or we can say 4 bytes. So that means from here we will get the number of blocks available in our RAM, or the main memory. Number of available blocks are available in our main memory. So each block can accommodate 4 words, and our total is what? 128 words. So that means what? If we divide, then we will get 32. That means this 32 is what? This 32 is the number of blocks available in our main memory. So that means 32 blocks will be available in our main memory. 32 blocks. And this block index should be start from 0. This block index should be start from 0. Now B0 is what? From B0, that means 32 blocks. So that means 0 to 31. So block number 0 to block number 31. This will be present in our main memory. And each block can accommodate 4 words. So that means in block 0, which are the words will be present? Word 0, word 1, word 2, word 3. Then block 1, word 4, word 5, word 6, word 7. Then in block 2, word 8, word 9, word 10, word 11. Then in block 3, word 12, word 13, word 14, word 15. Then in block 4, word 16, word 17, word 18, word 19. Same like that. If we go in our last block, that is the 31th block, because we start from 0. So that means in the block number 31, what are the words will be stored in block number 31? 120, 128, 129, 130, and 131. Because sorry, 120, it will be 128 words. So that means this will be 124, 125, 126, and 127. And because from 0 it is also started from 0, so that means 0 to 127 words will be present. So the last block will contain word number 124, word number 125, word 26, and 127. This will be stored in our last block. So that's why it is stored into our main memory. Now the main problem is we cannot. Now in our nomenclature or in our architecture, we have seen some portion we have to brought into our cache. Some portions we have to brought into our cache. So that means from here the block will be transferred to the cache. But there is some problem. Now main memory can accommodate this large amount of words, but cache is not capable of storing that large amount of data. Cache speed is much more. Cache speed is much more than the main memory, but cache cannot accommodate this large amount of data in the main memory. So how? This is the problem, or this is what the mapping, that's why the mapping is done, that which block we have to accommodate the cache. That is why it is saying that how to block available in the cache and put it into which line. Now in cache, in main memory, we have seen that this main memory is divided as a block, but in cache, the cache memory is divided as a line. Cache memory is divided as line, and main memory is divided as the block. Now that means this is what, that how to make available this block into cache, and this block will available in which line of cache. We have to map that, and CPU will generate some address to make reference to the address to the cache to get that particular data, because CPU is accessing from cache. That means which word CPU will generate address, and this address which this will be to reference to get the data. So which data it will get, this is the mapping. So now in cache, you see cache can only accommodate 16 words, whether this main memory can accommodate 128 words, but cache can accommodate only 16 words. So that means we have to move the block in such a way that it can accommodate into the cache. So that means 16 words can this cache can available, or this cache can accommodate only 16 words. So from here, the number of lines will be what? The number of lines in cache will be 16, and we are considering each line can accommodate 4 blocks, because from here one block will be transferred to the our line, the next block will be transferred to the line of the cache. So here the number of lines will be what? The number of lines will be our total number of words present into the cache divided by the number of blocks accommodated per line. So number of block accommodated per line is, we are considering here 4. So that means that's why it is 4 present. So that's why the 4 lines are present: L0, L1, L2, L3. Okay, so that's why like this, same as block, we divided the block. Here also in cache, we have divided this cache into the number of lines. So from L0 to L3, these 4 lines are present into the cache. Now the main thing started. Now which block? The block we already seen that there are 32 blocks. Now between these 32 blocks, which block will be accommodated to which line? Which block will be accommodated to which line? We can know using this formula: K mod n. K mod n. Now K is what? K is the number of blocks, block number. K is the block number, and n is the number of lines. So first, our first block is 0. So that means K is 0 mod n is number of lines present in the cache. That is what? How many lines are present? L0, L1, L2, L3. That means 4 lines are present. So 0 mod 4. If we do 0 mod 4, that means what will be the remainder? That is, if we divided 0 divided by 4, then there is nothing remainder. That means 0. So the value will get 0. That means 0 means what? Block number 0 can be accommodated into the line number 0. Block number 0 will go to the line number 0. Then next block B1. This B1 block will do what? This B1 block means 1 mod 4. So that means 1 mod 4 means what? If we divide 1 divided by 4, then what value we will get? 1. We will get value as 1. So that means our block 1 will go to the line number 1. Then next, if we do 2 mod 4, block number 2, that means 2 mod 4. So that 2 mod 4 is what? 2 mod 4 means our remainder will be what? If we divided 2 divided by 4, then our remainder will be 2. So that means block number 2 will go at line number 2. Same procedure, block number 3 will go to the line number 3. Then again block 4. So 4 mod 4, that means remainder is 0. So that means block number 4 will go to the L0 again. Then block number 5, then block number 6 will go to the, with using this formula, K mod n. Using this formula, we will do what? We will accommodate the blocks into this particular line. Now, if we go like this, then all the blocks will be present. The block is what? This block will go, that last block, the last block that is go, that block number 28 will go to the line number 0. then 29 will go to the line number 1, then block number 30 will go to the line number 2, and block number 30 will go to the line number 3. So this is how a block will be accommodated. This is how the block will be accommodated into the cache. And here we are considering that the line size which is present, that means the size of the line, that at a particular time in a line, how many blocks can be available. This is the line size equal to block size. That means particular thing is what, that block size equal to line size. That means in a block we can accommodate at a time 4 words. So that means what, in a line we can also accommodate at a time only 4 words. Now 4 words means what, only a block will be present, because if we consider, let's say, if we consider our block size, let's say B0, in B0 blocks 4 word is present. Same as that for line size, because line size is equal to the block size. That means L0 can accommodate only these blocks, B0, B4, B6, B12, then B4, B8, then B12, then B16, block number 16, block number 20, block number 24, block number 28. Only these blocks can be go to the line number 0. This is specified with this formula. That means if between any of this block that came now in the cache, then we directly accommodate it into the line number 0. We will directly accommodate this block into the line number 0. But it should be keep in mind that at a time the cache can accommodate only a block. That means if in a cache B0 is present in the L0, that means in line number 0, let's say B0 is present, this block is present now. Then let's say another block came, B4 block came. Now B4 block has to be allocated in the line number 0 only. In the line number 0, the block 4 should be accommodated. But now in our line number 0, block number 0 is already present. So we cannot do that. So when the block number 0 will complete is everything working, then only we can accommodate block number 4, our next block. So this is what in this the direct mapping thing, that now we will accommodate the next block. So at a time, we can say at a time a cache can accommodate only one block. Okay, so if the block number 1, block number 5, block number 9, block number 13, anything came, then let's say in B0, after B0, B4 next block in is came. So let's take an example. If like this, let's say this is the block, and in this block, let's say the same example we are taking in line number 0. This is the line number 1. This is our line number 2, and this is our line number 3. Now let's say the first block B0. So we perform K mod N and find that the remainder is 0. So that means the block 0 will be accommodated into this line number 0. The next block, let's say the next block that came to the cache is B4, the next block. Now that is what this B4 next block came, but we cannot accommodate B4 now. Whether there is empty, if you see line number 1, line number 2, line number 3 is empty, then this is what you can say that, sir, can we use in the B line 1, line 2, line 3? We can accommodate that because they are empty. But this is the problem of direct mapping, that whether it is empty, then also we cannot accommodate it, because B4 is directly specified that it will go only in the line number 0, only in the line number 0. But line number 0 is already has a block there. So that means when this block will be removed, then only we can accommodate the block number 4. So this is the problem of the direct mapping, because here with this formula we have specified that which block should go to the which line. So this is the problem, or this is the disadvantage, a first disadvantage of this our direct mapping. Okay, clear?
Yes, sir.
Yes, sir.
Okay, so this is what our direct mapping. Now we will see that how the CPU will generate address. The CPU, now main memory is what? Main memory generates, our main memory generates physical address. Our physical address is generated by the main memory. Now if we see in the example, we have seen that our main memory is 128 words, or let's say 128 bits, 128 bits. Now, to accommodate 128 bits, how many bit is to be used to represent this 128 bytes? How many? How many is required this 128? If we see this 128, that means 2 to the power 7. That means 7 bits are required to represent this 128 bits. Because 2 to the power 7 is equal to 128. That means to represent 128, we require 7 bits. That means our physical address of our main memory is what? The physical address of our main memory is 7 bits. Our main physical address of the main memory is 7 bits. Now, this 7 bits is what? Between these 7 bits, this 7 bit is divided into two, part. One is the block number and another one is the block offset. So if we take this example, this 7 bit is what? This 7 bit is divided into two part. One is what? One is our block number and another one is the block offset. Now, what is the block offset? Block offset means the block size. Now, we have already seen that each block can contain 4 words. Each block can contain 4 words. That means to represent 4. How many bits we have required? 2 to the power 2. That means 2 bits will be required to represent this 4. So, block offset size is what? It will be 2, because to represent 4, because we know that each block we are considering that it can accommodate 4 words. So to represent this 4, we have to require 2 bits. We have to require 2 bits. So that's why it is 2. And that means if 7 minus 2 happen, that means the block number will be what? The block number will be 5. 5 bits. The block number will be 5 bits. So that's how our total physical address is divided. Now let's say CPU generates an address. CPU generates an address 0001010. This is CPU generated. Now this first 5 parts, because we already seen that last 2, that means 2 bits is for the our block size. So that means last 2 bit will be for the block size and the first 5 bits will be for the block number. First 5 bits will be for the block number. Now 10 is what? First block number is 00010. That means that this is what? This is representing the block number. So 00010, that means what? That means 2, because if we convert it into the decimal, it represents what? It represents 2. Now that means we have to go to the block number 2. So in the block number 2, we have to go to the block number 2. And block number 2, what is the in 0 0 0 1 0 1 0. So this last 2 bits, what this represents the block size, and this is representing the block number. So if we convert it into the decimal form, it represents what? It represents 2. That means we have to go to the block number 2. Okay, so we go to the block number 2, and last 2 bit is representing the word. Last 2 bit is representing the word. This 10 means what? This 10 means 2 also. That means in block number 2, the second word we require. So that means we have already started it from 0 1 2. That means 0 1 2. If we take, that means word number 10. Word number 10 is required for the processing. That's how we will find, because in block number 2, these 4 words, in this from 0 we will consider, so 0 1 2. So in block number 2, the word number 10 is required. So this will go to the our CPU. Okay, so that's how to mapping from CPU with the main memory. In next class we will see that CPU will map with the, how it will map with the cache memory. Okay, clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so then thank you everyone. In
Thank
next
you, sir.
class we will see about that how the mapping between the cache and our CPU can be done. Okay, so thank you everyone. I am ending the session.
Thank you, sir.
Okay.